Last episode we focused a lot on stacks or zippers and stack sets and watched them change over time as xmonad's state changed. And I mentioned that if you haven't seen this exclamation mark before, that we'd get to it later, and now's that time. But first, let's understand what a stack is holding. We saw a stack being printed out as numbers, but this definition of a stack is polymorphic. It doesn't actually care about what's being stored, as long as it's the same type for the focus and the up and down lists. But in the case of xmonad, it's actually storing a window, and a window is defined in the X11 library as an XID type, which happens to be a word 32, a 32-bit word. And that's why we saw them printed out as integers. The exclamation mark is a strictness annotation. It tells the compiler that we want to evaluate whatever's being stored in the focus. You may have heard that Haskell is a non-strict language, and that means that expressions are only evaluated when they're needed. So it's possible without the strictness annotation here that instead of storing focus values such as the window identifier, it could be storing an unevaluated expression like the head of a list of windows. And doing that is going to take more memory than just storing a 32-bit word. So let's try profiling xmonad itself now. To do that, I've written a simple profiling script, xmonad bench, that opens up 10 xterms, stores the PID of each in an array, and then after pausing for a couple seconds, kills each of the xterms that it starts. It's not a benchmark that's representative of normal workflow in a window manager, but it'll give us something to use. So to profile xmonad's memory usage, there's a runtime system option that you can use, but you have to compile xmonad with runtime system options enabled. So let's do that now. Let's give ourselves some space to work with. And cabal dev install. There's a flag cabal install arg, which allows us to pass arguments through cabal dev to cabal install. And then we'll give a GHC option. So this is kind of two layers of indirection here. RTS ops. And to keep cabal dev from complaining, we'll force reinstalls. We also don't want xmonad to launch a version we compiled elsewhere in our .xmonad directory, so let's hide that for now. And now we should be able to launch xmonad with the profiling options from the cabal dev directory inside of the source. So plus RTS -s. So now xmonad is running. The line that says execute file does not exist. It's exactly what we want. And we can start the benchmark, xmonad bench, which creates a number of xterms and then gets rid of them. So we'll quit xmonad. And you can see that about 4 megabytes were allocated on the heap, and the maximum amount of memory that the program was using was about 80 kilobytes. And we can compare this against xmonad without the strictness annotations. I went ahead and prepared a copy of xmonad with all strictness annotations removed ahead of time and put it in xmonad non-strict. So let's try the same command here. And we'll run the benchmark again. and quit xmonad. And you can see similar results. What's interesting is that there's actually less memory allocated in the non-strict version. And this confused me the first time I saw it. Surely the strict version was going to use less memory. But then I realized that all of the windows that are being created and then destroyed never receive focus, so that may not be the best type of benchmark. And if you were to slow down the benchmark and focus other windows, you'd see that the strict version does have a slight edge over the non-strict version. Now, I looked through the source for some more interesting code to show you, but it turns out that xmonad is a pretty small program, and most of the interesting code relates to talking to x11 through xlib, and that's pretty specific code that most people aren't ever going to write. Instead, what I think makes xmonad interesting is the ability to extend it, since the configuration file is really just a Haskell program. Let's say that in a normal workday, I have xmonad open, and I have three windows, three xterms. And in the first, I'm browsing Haskell Reddit. In the second, I'm working on some code in, let's say, Vim. And in the third, I'm playing a game like Rogue, which didn't work for some reason, but you can picture it there. And rather than make a decision on what I should be doing, I'd like to have some sort of roulette wheel that spins the focus around and lands on one of these windows and decides for me what I'm going to do. Let's try building that in xmonad. First, we'll make a new xmonad directory, and then we'll create a xmonad.hs. So we'll call the function to spin the roulette wheel roulette. But what's the type of the function? And how do we write it? Basically, we want to just move the focus down some random number of times. Already we know that xmonad has a way to move the focus down once with mod j, so we should be able to look at what the code for that key binding does and model our modification on it. So let's check the source for xmonad, and it should be located in config.hs. And last we looked at this, we were looking at the workspaces, but let's look for focus down. And here it is, bound to both mod tab and mod j. And all it is Windows and then w.focus down. Well, W is imported qualified stack set, and Windows is declared in operations. And it's a function that takes a function that maps a window set to a window set in the xmonad. Now, we don't actually have to know how that works because we're just going to be calling focus down, which does the work for us. So let's import a stack set in the same way. And roulette will be an action that runs in the xmonad. To start with, it can just be focus down. And we'll import xmonad. Now, to actually call roulette, we'll need to bind it to a key. And the syntax for that is a little bit complicated. But fortunately, there's an easier way through xmonad's easy config, which is in the xmonad contrib package. And there's a function additional keys p, which takes a string in the same format as you'd see in an Emacs config and binds the key. So we'll use that. Additional keys p, and we'll bind it to the mod character and r, roulette. And now let's compile that. Xmonad recompile. And oops, I forgot to import easy config. And again, I got the name wrong on that. And now we can restart xmonad with mod q. And let's try our new mod r binding. And you can see that it has the exact same effect as mod j or mod tab. Now let's make this behave like a proper roulette wheel. Instead of just moving the focus once, let's move it a random number of times. To repeat something some number of times, we can use replicate m from control.monad, where I is some number of iterations. And we want I to be a random number of iterations. And in Haskell, random is not a pure function because it doesn't have the same result every time you call it. So we'll use random RIO between, say, 7 and 14. And random RIO is an action in the IO monad, so we need to lift it. And now let's try recompiling. Oops. I always forget to import the modules I need. Let's import system.random. Restart xmonad. And now when we spin the roulette wheel, we end up at a random window. But the action's happening too quickly to see, so we need to introduce a delay. So let's do that with thread delay. And thread delay takes the number of milliseconds, the number of microseconds to delay. So we'll just delay 100,000 microseconds. And that's part of control.concurrent. And we also need to lift that. And let's try again. And restarting xmonad. Now let's run roulette. And you can see it working. But the wheel is spinning at a constant speed, and I'd like to make one more modification just for fun. And that's to use the Fibonacci sequence to simulate the wheel slowing down. It may not be the correct model for the deceleration of a roulette wheel, but I've always seen the Fibonacci sequence illustrated in Haskell tutorials, and I've never seen it actually used. So it could be fun to actually use it. So the Fibonacci of 0 is 1, and of 1 is 1, and of n is fib n subtract 1 plus fib n subtract 2. And we'll use the Fibonacci sequence instead of a constant delay here. So using a list comprehension, we can take fib x of x from 1 to I. And rather than replicate M, we can use map M. And we'll call the new action spin of focus on this list. So let's change what we have here to spin of focus equals do. Spin of focus takes a delay value, and we'll delay by, say, 1,000 microseconds times the delay scaling factor. And let's compile that. Oops, got a parse error, which is because I didn't properly format this. And now we have another error about something not being specific enough. Which is probably caused by me not having type annotations on anything. So there we go. So let's try spinning the roulette wheel one more time. And it's still a little bit fast, so maybe 10,000. And now the roulette wheel is a little bit slow, but you get the idea. And with that, we've customized xmonad, and it didn't take very much code. If you're interested in more xmonad extensions and customizations, take a look through the xmonad contrib package. I hope you've enjoyed the tour of xmonad and seen how you can build a monad that encapsulates state, and you can examine that state while the application's running. And also seen a way that xmonad can be customized that might inspire you for how to add customization to your own project. We also took a brief look at strictness and how it can affect the performance of your program. But I want to stress that you shouldn't worry about it until you actually run up against it with one of your own programs. In the next episode, we'll be taking a little break from Haskell for a while and taking a look at some popular JavaScript projects. Thanks for watching, and I'll see you then.